Okay. Hi, everybody. I'm Greg Karras. I work for CBE. Communities for a Better Environment builds grassroots power to achieve environmental health and justice in and with communities of color and working class communities. We use organizing, legal advocacy, and science to do that. We're unique in being a community-based nonprofit environmental justice organization that has those three capacities in-house. And as Sherry said, I'm a senior scientist with CBE. I've been working on these types of issues, including on refinery and other energy issues, for some 30 years now. So jumping right into it, this chart, and I should explain a few things about this. This chart shows emissions of CO2. The taller the bar, the more the emissions. And it shows emissions across 97% of the U.S. The colors, you'll see them in other charts, so maybe I should explain those right up front. Yellow is the East Coast region of the U.S., PAD 1, for those of you who define it that way. Blue, Midwest. Orange is the Gulf Coast around Texas, Louisiana. Black is the West Coast, which includes California, and then California is broken out, red on the right. The other thing about this slide is it's showing emissions per barrel or per volume of oil refined. Here it's showing them per cubic meter. Refineries, of course, are of different sizes, so this comparison accounts for that. And most of the comparisons that I'm showing you, maybe all of them, will be showing per barrel or per cubic meter. So, you can see that burning fuels for process energy emit CO2 and other pollutants. But some refineries emit more than others. Here, the range from the highest emissions to the lowest, the highest are 56%, and that's across whole regions and years. Why? Why is that? What causes differences in refinery combustion emissions? Can it be verified by real-world data from operating refineries, direct observations of what's actually happening? And can we predict how much it could increase or decrease emissions? So those are the basic questions that this research that CBE did, and the follow-up research specific to California that we did with Union of Concerned Scientists. And I want to shout out to Jasmine Ansar from UCS, who's here. They collaborated in the second part of the study. How we did it. Factors affecting refinery combustion emissions were identified using petroleum engineering knowledge. Publicly reported data on these causal factors were gathered from refineries in actual operation across the U.S. over 10 years, in California over 6 years. Around 5,000 annual average observations, each of those accounting for multiple refineries over the course of a year. It's a lot of data. The data were analyzed to quantify the contributions of the causal factors and combinations of factors on refinery emissions. This research was peer-reviewed and published by the American Chemical Society and by the Union of Concerned Scientists. So the data, crude feed quality data, let's start there. This chart shows, for the same regions and years, the density and sulfur content. How heavy is the crude is the total length or height of the bar, and the black part is how much of that is sulfur. So oil quality was defined in this study as the density and sulfur content of the crude feeds, the feedstock into the refineries. And you can see that it varies by almost 8 kilograms per cubic meter for sulfur and more than 40 for the density of the crude among the regions and years. So to put it really simply, I'm going to say something that Tom just said in just a little more detail. This is a simple block diagram, 2 refineries. Refinery A and B, they both are refining the same volume of crude oil input. Refinery B, the bottom, is refining lower quality oil. More of the lower quality oil goes through aggressive processing in refinery B. That's the big box in the center, much bigger. More of the flow goes through that box. The extra energy for that added processing makes refinery B burn more fuel for every barrel refined. So the engineering science tells us basically that refining denser, higher sulfur crude requires putting more of the barrel through aggressive processing that burns more fuel for energy, increasing emissions. And the processing intensity data, to get a bit more into the details, crude processing intensity, PI, was defined as the ratio by volume of vacuum distillation, conversion capacity, that's catalytic, thermal, and hydrocracking. That includes coking. And crude stream, this is gas, oil, and residual hydrotreating capacity, to the atmospheric distillation capacity of the refinery. How much? So it's what ratio of all of that and each of it to the total capacity for crude to go into the refinery. And as you can see here, it varies by almost 80% from top to bottom among the regions and years. Energy intensity. You can think of this as energy efficiency as you're comparing the different presentations. In this study, it was defined as total refinery process energy consumed per volume crude feed, and it's based on actually reported fuels consumed. It ranged by more than 70% among regions and years. So to recap, petroleum engineering knowledge tells us that refining lower quality oil requires increased processing intensity. This increases refinery energy intensity, and that increases refinery emissions by burning more fuel for energy. And real-world data, observations, reveal substantial differences in each of these variables among refining regions and years. So the next question, can this causal factor be verified using analysis of these real-world data? So I'm going to show you a series of these. Observations, actually observed data, are on the vertical axis. The higher, the more. In this case, it's processing intensity. And as you go from your left to your right, the crude gets denser, higher in sulfur, or both. And so that horizontal axis is showing the processing intensity predicted by the analysis. And you can see they line up pretty well. Oil quality can explain 94% of the differences in processing intensity among regions and years. And this is for the U.S. data. Pretty much the same with energy intensity. It's strongly and positively associated with process intensity. It can explain 92% of the differences, process intensity can explain 92% of the differences in energy intensity among U.S. regions and years. And so there's your mechanism, is the processing intensity that Tom also talked about. And here is energy intensity compared to oil quality. Also strongly and positively related. Oil quality can explain 90% of the differences in energy intensity among regions of years. This is based on the U.S. data. And including the California data and also accounting for potential nonlinear relationships between variables using in this case, non-parametric regression analysis. You can see that includes more information. There's a wider span of crude quality and energy intensity. The red dots in California are out there. So that's more information. But the same general concept holds, and the data the results stronger. Energy intensity remains strongly and positively associated with oil quality. Oil quality can explain 97% of the differences in energy in this comparison. And then emissions, also including the California data, remain strongly and positively associated with oil quality. Oil quality can explain 96% of the differences in emissions among regions and years. We spent a lot of time looking at other factors, and these differences could not be explained by other factors in this data set. The fuel mix. For CO2 emissions, the impacts due to dirtier burning fuel mixtures are not significant in the strong relationship between refinery energy and emission intensities. The same refining byproducts, coke and fuel gas, are dominating emissions from fuels burned across these regions and years, so that makes some sense. For capacity utilization, refineries were running pretty close to full capacity across regions and years, 81 to 95% capacity on average. And differences in the portion of refining capacity used are not significant in the relationships between energy intensity and oil quality. Refined products, we looked at this in more detail, but the summary conclusion, and this was quantified, differences in refinery product slates among these regions and years, they're not significant in strong relationships between refinery energy intensity, process intensity, and oil quality. As Tom said, it does matter whether you're making more gasoline or not. That does require more energy. So we looked at this in more detail. And for products, here are the things we found. In each case, as oil quality input worsens and emissions increase across regions and years, the yield of the main refined products, gasoline, diesel, and jet fuel, changes little or declines slightly. It doesn't change that much, while the oil quality, emissions, the energy intensity changed a lot. And there's incomplete conversion. You crack heavier oil harder, you're going to get more byproducts. That limits to some extent how much gasoline you can get out of it, no matter what you do. So, and in fact, there was a tendency for the gasoline and distillate yields to decrease slightly. They weren't processing more of it downstream, because they weren't getting more of it out even from the additional cracking. And the capacities of the major processes that act on those product streams versus the upstream crude processes, crude stream processes like cracking, coking, vacuum, that aggressive processing, their capacities changed little or decreased slightly. They weren't processing more, so they couldn't be responsible for these big increases in energy and emissions. Product hydrotreating, in fact, was shown not to be the factor, and hydrogen production energy was increasing to feed increased hydrocracking as the oil input got denser. And then finally, there are a couple of different ways. We looked at two of them in the two different studies we did, where folks at National Environmental Technology or Energy Technology Laboratory and other independent researchers have tried to figure out how much more energy does gasoline take than diesel to make, if everything else equal. Applying those data, the emissions calculated from differences in fuels alone actually changed little and decreased slightly as the total emissions increased and the oil quality got worse. So we were able to exclude those other factors. To recap, oil quality is the major driver of differences in average refinery CO2 emission intensity, and now this is verified. And I believe this is the first peer-reviewed study to do so. This has been verified against actual observations of operating refineries in the real world from major U.S. refining regions in California over multiple years. So, how accurately can this analysis predict increasing CO2 emissions from refining even worse quality oil? For example, if we didn't already know what the extreme high, in this data set, the California average is the extreme high emissions. If we didn't already know what they were, would we be able to predict them based on the crude feed quality? You can do that analysis by just not telling the computer, by withholding the data that you know about what the emissions actually are, just telling it everything else, the crude feed quality, the products. And we did that for California, and this graph shows it. The white circles are the data where everything was in there. That's what's the models calibrated on. Those are the U.S. data from the four major U.S. refining regions. The rest of them are California data. The orange diamonds are annual averages for California. You can see that they cluster around the line that's the predicted increase in emissions. On average, across the whole 6 years, they're within 1% of the line. We were able to look at some Bay Area refineries and the Bay Area average. 4 of those refineries, and I'll just say it, number 3, the one at the top, that's Shell. They're refining a pretty heavy crude slate. 4 of the refineries line up with the line that the emissions could be explained by oil quality in this analysis. And these are emissions that were reported to the Air Resources Board by the companies, and then adding in the hydrogen plant emissions where they were using a third-party hydrogen plant. The one that is different, number 1, is actually the Chevron Richmond refinery. I'll come back to that. So, predictions versus observations. Here's the key points. Predictions are relatively accurate for average CO2 emissions from large multi-plant refinery groups with diverse well-mixed feeds. the example here, the crude feed density and sulfur contact predict long-term average California refinery emissions within 1%. Analysis of individual refineries, however, needs to consider other factors, other properties of oil, refinery equipment and its efficiency, products and/or fuels. And the example would be the Chevron Richmond refinery. That's the one data point that we had where the reported emissions are higher than you would predict from the oil, and it was outside the significance of the model. So, overall predictions. What if we went to the lowest quality oil? What if we brought the tar sands or the heavy crude from Venezuela here in the state or the country and refined that? And this would be the extreme example, 100% of the slate going into refineries. On average, the increase in emissions from what is happening on average now is about 2 to 3 times, and the error bars there, the gap in each case shows the 95% confidence of prediction. But overall, it's about 2 to 3 times more emissions than now on average. The red bars show you some comparison, the U.S. average, California, which, as I said, is higher, and then the Martinez refinery, and those are observations. So it shows that while what the black bars are inevitably an extrapolation at this point, they're somewhat supported by the fact that we have observations, whereas you get to the heavier, higher sulfur crude inputs, we're seeing refineries that, in Shell's case, are approaching some of those. The implication: use cleaner, not dirtier energy resources. We need to keep going in the right direction, not go backwards. For climate, these findings support the high estimates, the high end of estimates by others, of emissions from extracting and refining low-quality oil, both at the well or the extraction site and at the refinery. Emissions increase, and together, those estimates raise the possibility that a full-blown switch to much dirtier oil could impede or foreclose total efforts from all sources to avoid severe climate disruption. So this is important. And that's talked about a lot now, which is good. For health, though, I don't think there's enough talk about this yet, and this study did not quantify it at the emissions days, but burning more fuel to refine lower quality oil emits toxic and smog-forming pollutants along with CO2. That's obvious, right? You burn more, do nothing else, and you're going to get more of all the combustion products. But that's a big problem here and in other places where refinery emissions of these other combustion products already are causing disparately high and health-threatening exposures in nearby communities of color. So those are the major implications of this study in terms of what we do about it. Acknowledgements, again, I want to shout out to the Union of Concerned Scientists, and Jasmine is here, Jasmine Ansar, for their support and collaboration.